One of the difficulties we encounter is there are a lot of derivative rules. There are even more antiderivative rules. This is not a new idea. There are lots of things over here. So one of the issues we encounter is trying to figure out how best to undo our derivatives. And it turns out one of the easiest methods, after doing powers, the stuff we already have for trig formulas, just working our derivatives backwards, one of the easiest rules to work backwards is the chain. At first glance, I look at this, I say, well, oh, this is a polynomial. I just have to multiply it all out. 3x plus 1 to the 7th? I'll be here for a week. I don't want to do that. But this appears to be related to this. So it's almost like that's our extra bit that pops out when we do the chain rule. All right, wait a minute. If that's the extra bit that came out of my chain rule, then let's ignore it for a second. This is stuff to the 7th. That's how we think of it when we do the chain rule. We take the derivative of the stuff. So if I just think of it as stuff to the 7th, what's the antiderivative of stuff to the 7th? One-eighth stuff to the 8th. Let's take a look at that. One-eighth stuff to the 8th. If I take the derivative of this, all right, the 1/8 is a constant, it stays there. The derivative of stuff to the 8th is 8 stuff to the 7th. And then in the back of my head, I hear the infomercial. But wait, there's more. Order today and you get extra. A 6x. The derivative of the inside. Hey, these cancel, don't they? And that is exactly the antiderivative I wanted to give me the integrand. Antiderivatives, derivatives, and integrals undo each other. So when I take a derivative, I should get back the stuff that's in the antiderivative. Great. I like this. Let's formalize this a little bit. I don't want to just guess my antiderivative. I want to have a method for recognizing it. And I go back to the labels we used when we did the chain rule. We thought of this as a composite function, f of g of x. And then we gave f g of x, we gave that g of x a letter on its own. So I'm going to consider this piece, the g of x we were working with, And then I can think of f of stuff as stuff to the 7th. Back in chapter 3, when we did the chain rule, I gave that a letter. Tried to be funny about it. U, right? FU. So we're going to FU here. But I might as well go ahead and use that letter up here. So I can think of, instead of writing this as G of X, I can write that as U. You can use any letter on the face of the planet. I don't care. I just don't want to use X. I've already got an X. And then I'm saying, oh, this piece is somehow the derivative. So let's write the derivative. If U is 3x squared plus 1, then my derivative, and I'm going to use Leibniz on purpose here. I'm going to write this not as U prime, but as du dx. Derivative of 3x squared is 6x. How does this help? Chapter 3, section 10. Differentials. I'm allowed to treat du and dx separately, like they're different pieces in a fraction. Take the dx from the left and move it to the right. I've rearranged my differentials. That's even what we called it in here, right? We had the integrand, we had our differential. Well, now I have a differential in terms of u instead of just an x. I'm going to take our original integral. And I'm going to rewrite it in a different order because I'm multiplying. It doesn't matter what order I multiply the 6x and the 3x squared plus 1 to the 7th. And now I'm going to turn everything in this integral from x to u in one fell swoop. Change the letters. U equals 3x squared plus 1. So 3x squared plus 1, quantity to the 7th is u to the 7th. And my differential takes its toll. Now we do the antiderivative. That's just power rule. I like power rule. What's your antiderivative? In u. Thank you. But I started this problem in x. I should finish it in x. So go back and put our expression in x back in for u. Isn't that the same antiderivative we got before? We just wrote it with the 1/8 out in front instead. It's the same answer. Perfect. This differential analysis that we've done here allows me to change completely from one variable to the other. Mixing letters is a pain in the ass. I don't think it's worthwhile. Please make sure you don't do it. You'll see in several online references, people have all sorts of integrals with different letters in different places. No, it's either all in x or all in u. I don't know how to do mixed variables at this point. That's Calc 3. Save it for later. Questions? Yes, ma'am.
Can you just go like step by step?
Sure. Well, let me do another one, exactly the same setup. We'll walk through it. My goal is to recognize inside and outside for the chain rule. And then when I switch from one letter to the other, I'm just doing a simple antiderivative. Now, what's important is that I am looking for an outside and an inside that are related, like our U and our DU pieces hopefully are. Do you see such a thing here? Okay. I see cosine of stuff, and then I see exactly the derivative of that stuff on the outside. Those are my related pieces. So I can say, all right, if U is x to the fourth plus 2, the derivative of that and then I rearrange my differentials, and I notice that these two pieces are being multiplied. So I can reverse their order. And then that becomes the integral of cosine of U du. What's something whose derivative is cosine? Except in this case, we're all in U. But if I start in X, I should end in X, flip back your substitution. Better, Jen? Wonderful. Questions?
So you subbed in 4x cubed dx. Yeah, right there for, did you sub that in for, how did you sub that in for dx if it is equal to du?
I didn't sub it in for dx. I subbed this whole piece to this whole piece. I subbed it in for du instead of subbing. The whole idea is to translate into the new letter.
Also change the dx to du.
I want everything in terms of u, and I need to adjust the differential. Otherwise, this won't work. I'm a very visual person, so I don't know if this helps or not. When I think of that, you could get out your calculator, you could graph this, right? Please do. I don't know what your picture looks like. But when I graph this, that's my x-axis, right? When I make this substitution, I'm literally changing the axis we graph on. So instead of having x and y, I want to have U and Y. Little bitty differences in X is how we make our rectangles, right? So the width of a rectangle up here would be a dx. But the width of a rectangle down here is different. It's a du. And so I have to adjust to accomplish this transformation of my picture. Your picture, I don't know what it looks like, but my picture looks like that. Because when I switch this with this substitution, I now have just e to the u. And that's a graph I know. But the width of a rectangle on my page is not the same as the width of a rectangle on your page. And so I have to adjust that width accordingly. One of the analysis textbooks I have calls this frame stretching, which just sounds weird until you realize they stole the term from the physics people in relativity theory. We're getting up there. Hey, I know how to do the antiderivative. What's the antiderivative of e to the u? That was easy. Which means the antiderivative of this is done. Better? It doesn't always work perfectly. It would be nice if I could rig this and it would work exactly perfectly every time, but it doesn't. Same problem we just did with a little twist. Something is missing from the version we did before. The constant is missing. There should be, to make this work right, 2x. But I don't necessarily know that in advance. The fact that I did the problem previously and can look and go, oh, that's how different those two are. If I had never shown you this, we might have a problem. So I'm going to do this blindly. I'm going to assume that I want to do a substitution up here. Let's write out the new differential. The derivative of x squared is 2x. I move the dx over and I get du is 2x dx. Now you have two different options at this point. We can mess with this, or we can mess with this. I'm going to do it both ways. The first option is to mess with the integral over here. I need a 2. I don't have a 2. I'm not allowed to just shove a 2 in there. The only thing I'm allowed to multiply by that doesn't change stuff is, so I'm going to multiply by 1. But I'm going to do it by multiplying by 2 and multiplying by a half. I'll put the 2 on the inside and the 1/2 on the outside. Because you can move a number across. When you have a constant on the inside, you can take it out. So I can think of having the 1/2 and the 2 next to each other, and then just pulling the 1/2 out front and leaving the 2 behind. The result, when I do this substitution, looks exactly like what we want. But I have this extra 1/2 out front. Big deal. It just stays there. It's a constant. I can do the integral without the constant. Leave the constant there, do the antiderivative. And now my answer shows up with a 1/2 in it. Option number 2 is to mess with the differential back here. But before I do that, are there questions in this part about sticking the constant in and out in the integral itself? We have this. And I say to myself, I don't have a 2 here. I have an x and a dx, I just don't have a 2. So I'm going to move, as I move the dx from this side to this side, I'm going to move the 2 to this side. And the x and the dx is what's in the integral right at the moment. So here, when I make the switch, I get e to the u, and then x dx gives me 1/2 du. Instead of the 2x, I didn't have the 2, so I put in the 1/2. But a 1/2 is a constant. I can take it out front. And lo and behold, that's exactly the same place. Which means I'm going to get exactly the same answer, regardless of whether I mess with the integral itself or if I mess with the differential. My preference is the second one, but that's the way I was taught. You do it whichever way you think fits you better. They both work perfectly the same way. As long as we are only adjusting for a constant. Because back on, what was it, page 470, whatever it was with the table, it said we take a constant in and out. It said nothing about moving letters. If I don't have the right power, I'm in trouble. So if I was looking at a problem like this, fine, you go mess with me, fine. This time, I can't do it. Yes. Thank you. Our method of substitution only works if we at least have the right power or right term sitting out there. I can adjust for a number. Numbers are fungible. Variables aren't. Questions? There are lots of other techniques, one of which would be useful for this. We'll get there. Not this one. Frequently, the difficulty comes in figuring out what we want to use for u. What's our actual substitution? There's nothing on the outside. Let's see if we can make this work with the inside, because the square root of stuff I might be able to use. Let's try. Wait a minute, what's the derivative of 2x plus 1? That's just a constant. Constants I can mess with. Yay! This is workable this way. And again, we can adjust either over here or over here. I'm used to doing it over here. So I'm going to rewrite 1/2 du equals dx. I move the dx from the left to the right. I move the 2 from the right to the left. And then my integral becomes the integral of the square root of u du with a 1/2 in front. I don't even need to put the 1/2 on the inside. It's a constant. I can put it wherever I want. I just put it out front automatically. Antiderivative of the square root of u. Because this is a power rule, it's u to the 1/2. Wait a minute, there's a 1/2 out front, so I'm going to get 1/2 still there, and then I'm going to get 2/3 u to the 3/2. That'll simplify. Cancel the 2's here in the fractions. And I start in x, so I end in x. Heads or tails? Heads or tails? When I can clearly see an inside and outside, that is my goal. Hey, let's do this as inside. That's under a square root, stuff, square root of stuff. Okay, right away, there's my visual trigger. I'm pattern matching to that same thing we see above. Let's see if that works. Does it work to let u be the stuff under the square root? Because I have the x, which is sitting on top at the moment. It can go with the dx if I move it over and just write 1 on top. Not moving stuff in and out of the integral sign, that's fine. I'm just missing this -8. So I'll rewrite negative 1/8 du is x dx. Finish this out. A square root in the denominator becomes and now I can do power rule. Add 1 to the power, I get 1/2. 1 over that is 2. Multiply those together, I get negative 1/4. 1/2 power is a square root. I started in x, I'll end in x. Questions? Sometimes it isn't obvious. I can't do the same thing we just did. Why not? I need an x somewhere if I want to use that whole thing under the square root. Well, I can't do that. Say again? Ooh. If I let u be the whole root, what's the derivative of that? That's a chain rule problem in and of itself, right? That's nasty. 1/2 1 minus 4x squared to the negative 1/2 times minus 8x. I'm not sure this gets me anywhere. Because I still have that extra x on the outside and I don't know how to adjust for it. Damn. Let's try again. All of a sudden, back of my head, I hear a voice in the wilderness. Formula sheet. Formula sheet? The formula sheet from the exam. Grab the formula sheet from the exam. It's 1/1/2. You add 1 to the power and you take 1 over the new power, right? For the power rule. So -1/2 becomes +1/2. -1/1. On the exam, you see stuff with 1 minus stuff in the bottom? Not only that, it's squared, isn't it? The derivative of the sine inverse of x is 1 over the square root of 1 minus x squared, right? I'm going to change letters. Big deal. No, because now I'm going to try and use that to do a u substitution. I think I can make this work if I let this thing be the u squared. If that's true, what's u? I got to take the square root of everything. What's the square root of 4? Aha. What's du dx? And I can fudge constants, can't I? So I'm actually going to take this integral and I'm going to write it as the integral of 1 over the square root of 1 minus 2x quantity squared. And now I can do my substitution. Oh, I have to rearrange my differential. So I get, again, 1/2 du equals dx. Because then I would not have the correct thing down there, would I? 4x all squared is 16x squared. And now this integral becomes 1/2 1 over the square root of 1 minus u squared du. Which is an antiderivative I know from the formula sheet. But I started in x, I should end in x. 1/2 arc sine of 2x plus c. So our u choice matters substantially. The way we choose to write u needs to be reflected in what's there in the integral. Sometimes I have to hunt for it. Sometimes it's hiding. The most common mistake in this problem right here is you go, oh, I got tangent. The answer is secant squared. Why is that wrong? You've made the same mistake just for something different. Unfortunately, the derivative of tangent is secant squared, not the antiderivative. I'm going the wrong way when I do secant squared. You gave me the derivative of secant of x, by the way, which is secant tangent. I can't go down. I got to go up. I got to make Power bigger. Can't do the derivative. I have to do an antiderivative. How the am I supposed to do this? There's nothing here for me to substitute. Except tangent isn't just tangent. Aha! Tangent is really two other trig functions. And those two happen to be related to each other. The derivative sine is, and the derivative cosine is, we have choices. What do you want to use for u versus du? Actually, yes, it really does matter. Which one did you want to use first? We can try both and see which one works. If I try sine, then du dx is cosine x dx. Oh, wait a minute, cosine x. Move the du over, and you get cosine x times dx. But the cosine x there is on the bottom, which means ooh, uh-oh. If I try and put the cosine on the bottom, and I'm going to get du over cosine of x. I can't mix my variables like that. That's bad. I could write it dx du. No, that's even worse. Dx du. I mean. If I think of the sine as the u part, the cosine should be with the du. So if I take the sine away, it would be 1 over cosine of x dx. These are not going to match. So let's try it the other way. What if I try u as cosine of x? Then du, derivative of cosine is, don't forget the negative. Now you'll notice I did the differential switch in one step. I didn't write du dx, I just wrote du and automatically put the dx on the other side. Okay, I just didn't write the extra step. If you want to, feel free. The more you do these, the more often you'll see we're always going to move that dx over. But what's missing? The negative. So either I move the negative over, I put a negative inside and a negative outside. Again, I either mess here or I mess here. Aha! Integral of 1 over u is ln, except I can't forget that absolute value. I started in x, I end in x. Yes, does help if I write the right one down. I love this answer. This is not the answer in the back of the book. Why not? Because the answer in the back of the book decides there's a minus in front of my ln. I don't like minuses in front of my ln. Numbers in front become powers when brought in. So they rewrite this as ln cosine of x to the minus 1. Wait a minute. Raising something to the negative 1 power does what? Puts it in the bottom. 1 over cosine. One over cosine is a secant. That's actually the answer in the back of the book, which is annoying as all. I would take this one. But if you go online and plug this into Wolfram Alpha, you're going to get the bottom one. What happens when I have a definite integral? Or they don't. There are two options again. Either I can switch everything. We already did this one. We know what the substitution is. I know that u equals 2x plus 1. And so if I was going to switch this, it'd be square root of u du with a 1/2 out in front. And we already did this antiderivative. Now, in the original integral, it says 0 to 4. Down here, it doesn't say squat. I have to choose. Either I have to finish the integral and go back to x, or I have to change the numbers. If I want to finish the integral and go back to x, which is what we did before, I would write x equals 0, x equals 4, reminding me that I haven't changed those numbers. And then when I finish the problem, which we already did, I end up here, and then I can plug in 0 and 4. And I get this lovely answer. What's square root of 9? 3 cubed is 27. 1 to any power is 1. So this is 27 minus 1, all divided by 3. That's 26 over 3. That's option 1. But option 2 is to do what I was describing in the picture, Chloe, and say if I'm changing from x to u, I can change the x-axis. And I can say, oh, there's my substitution right there. U equals 2x plus 1. So if x is 0, u is? And if x is 4, u is 9. And put those numbers here. Shifting my frame. I never have to think about x again. This problem is now all in u. I never have to go back to x. I do the antiderivative. And I plug in 1 and 9. And I get exactly the same answer. Now, again, it's a matter of comfort. I like shifting the limits, but it is not required. There is a pair of theorems at the end of this chapter about symmetry. You already used one of them in a problem you did for homework. You did the integral of 2x from -4 to 4. You all got 0 because the area under matched the area up. So they canceled out. If my function is even, then going from -a to a is the same as going from 0 to a and multiplying by 2. I like that because you don't have to put in negative numbers. But being even means the left side and the right side look the same, so you're folding it over. Take a look at the end of the section at the 2 pictures that go with this. It works really well. If you came in late, I still have your homework. Please come get it from me. That's part of our attendance today. I will see you all on Wednesday.